Morning, everyone. We've got 2 more lectures left to do for our course, and both are statistically oriented, and this is to help you move through activities 11 and 12. So this first one is tied to 11 and the second one more to 12. So ultimately we need to be able to calculate z-scores, that is to be able to compare our different measures if we have applicants that do, let's say, a battery of 6 measures or so, and they're scored on different scales. We have to find some way to combine those in some kind of meaningful manner, ultimately to rank order our candidates. Isn't that what we're all about? So let's talk about some of the basics here in the first one, and then more application of the basics in our second lecture. So let's orient ourselves. We're on module 3.23. We're going to talk about central tendency, variance, and z-scores. And so central tendencies, we talked about frequency distributions last time or the time before. And when we look at a frequency distribution, a histogram, bell curve, what have you, one of the things that we're interested in is the mode, and that is the column that displays the highest value, or if it was multimodal. Do you remember, if you have a multimodal distribution, what that might indicate? Okay, so if you have a multimodal distribution, at least 2 modes, what you need to consider then is you need to kind of enter in a second variable, ethnicity or gender, to see if your measures are creating adverse impact, and that explains the bimodality. So that's a warning sign, and that's why we look at frequency distributions to understand this. Believe me, if you have to defend a case in court, there's going to be people who present this information, so you better be able to speak to it, right? Because that's how these things are essentially determined. So central tendencies, the mode is the most frequent response in the distribution, and that shows the highest frequency. The median, right, is the middle value score, and we'll talk about that in just a second and how to calculate it. For example, if there's 11 values, the median is the 6th value in the list of values if they're arranged in descending order. I'll show you an example here in just a minute. I see Rosie's going to town on us. So, and looking at the, and the mean, we know what the mean is. We'll get to the mean here in a little bit. Now, so the median, what we see is, let's take a self-monitoring scale, for example. And let's suppose we're using self-monitoring, as we discussed in the previous example of sales reps, where self-monitoring might be a good predictor. So we're calculating, or we're giving our candidates a self-monitoring test, and then we're going to employ their scores in the selection process. So in this example, right, we have, let's see, 18, as I see it, we have 18 scores, 9 and 9, I believe that's correct. And what we do then is we arrange them in order. So we had 2 3s, we have 2 6s, whole bunch of 8s, right? Some 9s, some 10s, and we split this in half, and what we do then is look for the middle score. So for data that has an even number of items, you take the 2 middle values and you average them, and that becomes your median, as the average of those 2. So in this case, we have 9 and 9 this 9 and this 9 are the 2 middle scores, right? They equal 18, we divide it by 2, and that means the median in this case is 9. A little simpler if you have an odd number of candidate scores, because for data that has an odd number, the median is just simply the middle number, right? So what's of interest in this regard? Well, this is something that empirical scientists in social psychology, the median is used, personality psychology is used quite often in research. It is also useful to us in creating what's called a median split. And we've done some high versus low performers in our assignments. And one way we can get at this on the basis of actual scores is we can say, the top half of our sample then are the high scores, and the bottom half are our low scores. So we need to calculate the median to see where the sample is split in half, and then we can rank order those in the top half as the high scores and then the low scores. So we want to create 2 subgroups, and that's how we accomplish it. For the example, how do low and high self-monitors differ on sales performance? So we can look at them in the aggregate of those 2 groups, right? And we combine their sales figures and see if self-monitoring is a valid predictor of sales performance. Those below the median constitute the low group. Those above the median constitute the high group. And all is well. Now notice we do this with self-esteem. We might bring people into the lab and give them a Rosenberg self-esteem measure. And then we separate the people for statistical purposes into the highs and lows when we analyze the data. What we might do is then run them through a false feedback paradigm to see if people with high self-esteem react to negative feedback in a similar manner to people with low self-esteem, or if there's a difference. So we can compare the average score of both groups based on their self-esteem level coming into the laboratory. So that's a useful technique, and we can use it obviously to separate our candidates. But it's not without its detractors, and when you take a look at the median split kind of conceptually, it does become a little strange, right? You know, in this example of the self-monitors, right, we're looking at the same data set. Notice that the people who scored in this column now are going to be scored as low, and the people who scored in the higher column will be called high. So in this case, lows range from 3 to 8. 9 is the median, so we don't count those people right in the center, which is problematic in and of itself too. And the highs range from 10 to 18. But shoot, isn't it interesting that a low can be more similar to a high than two highs might be to each other? That is, if you look at, let's say, an 8 is a low and a 10 is a high, what's the difference? The difference is 2 points. But if you look, let's say, within either column, if you look at an 8 and you compare it to 3, the difference is 5. So you have a greater within category difference than you do possibly a greater between category difference. So often it's a trade-off, and we have to determine whether that makes sense or not. One way to kind of get around this, or to kind of lessen the impact of this, is we might engage in this process called banding. And meaningful difference split into bands. So the median here is split can allow us to take a continuous variable, which we had, continuous variable in terms of self-monitoring scores, right? And split it into two scores. In the previous examples, low would be scored as a 1, for example. So anyone who scored in the low column, we give them ultimately a 1 as a score. And then the people in the high band, we give them 2 as an ultimate score. But the two bands might conceal differences. So one way to get around this is to create multiple bands that is more than 2. So considering that scoring 29 is essentially the same as scoring 30. And this is especially certain when we go back to previous lecture on measurement error. What if our measurement, you know, shows error in the rate of plus or minus 1? So then let's do the math here that we have a 29 really is essentially the same score as a 30 if we're talking an error of plus or minus 1. So if the measure actually represents a score that's plus or minus 1 point, a 3-point band is not justified. That is grouping in terms of 8, 9, and 10 as one band, or 11, 10, and 12. So we need to know our margin of error, our standard deviation, when we apply bands, and we have to use it in some kind of logical manner. The bottom line is the difference between 29 and 30 meaningful in terms of future observed performance. And likely our measurements are not that refined, right? They're not that reliable necessarily, so that becomes a problem. So we incorporate bands as more a general statement of performance. So in this case, now we revisit what we have here. In this banding example, a score of 18 then puts someone in the first band. A score of 19 puts someone in the second band. And notice we've got the bands incremented in increments of 3, so we better have a relatively reliable measure here. If anyone scores between 16 and 18, a raw score, then their banded score we might call a 1. Anyone who scores between 19 and 21, we call a 2. And then on down to the highest band, which would be those who scored 20 to 30 as scoring a 5. So what we're doing is converting their raw score into a banded score as a result of this. Notice now what we're saying is, hey, we're not looking at all of our candidates in terms of 18 through 30. We're now looking at our candidates in the lowest band to the highest band with 3 intermediate bands. So it softens the blow of measurement error and the potential lack of reliability in a measure. And notice, we have to use a reliable measure. So when I say lack of reliability, I'm talking about the standard error. I'm talking about the measures of the lack of reliability in a measure. But it's still a reliable measure, just to what extent is it reliable? So consider that banding is always an option when we're looking at performance. And notice that when you did your repertory grid, when we looked at teachers as high versus medium versus low performers, what we were doing was subjectively banding these people for the process of developing the repertory grid. And notice that with those bands then, we chose that high and acceptable performers kind of then created a band in and of themselves that we used to compare towards the low performers. So it's this kind of cognitive flexibility when analyzing the data. Just think about what you're doing as you're doing it. Does it make sense for me to do it this way? Is there another way to do it? Are there any examples of how this has been banded before? Because remember, from your find a measure assignment, you might stumble into, and not stumble into, but diligently search for empirically validated articles where these tests have been used, and someone may have already done banding, compared different forms of banding, and then justified that banding for the validity of the prediction of on-the-job performance. So that this is all available to us, and that this is, I know that statistics and measurement are often students' least favorite part of studying a social science like psychology. But it's what gives us the greatest amount of power, really, in understanding concepts. It's one thing to theorize and develop opinions about it. It's another to collect data and then analyze that data to see what the data is telling us on the basis of statistical analysis as we become more objective. Now, you might counter right now and say, but you're banding and you're kind of assigning these bands arbitrarily, and that's awfully subjective. And I would say yes. But it might be subjective in the first part. As we go through some process of validating the bands, demonstrating that the bands are meaningful in predicting on-the-job behavior, notice then we're turning the subjectivity into objectivity. And isn't that kind of the core of hypothesis testing? Is I have a hypothesis, I generate a hypothesis, which is essentially my subjective opinion, and it might be a well-informed opinion, but on the way the world works, or measure works, or what we expect to see within an experiment. That's the subjective part, but once we put it to the test, that is, we carry out the test and test the hypothesis, we start generating data and we move from the subjective to the objective. This is one of the skills as you leave Ohio State, as you leave the Arts and Sciences program or business program, whichever program you're in, medical school, what have you. We need to learn to do this. This is a core requirement, is understanding the relationship between the subjective and the objective. Not that one is good and one is bad, but how they are, how they work together. Now, the other standard, the other measure of central tendency that we hadn't talked about yet, and we need to discuss at this point then, is the mean, because this is something you'll need to use also in your activities. So the mean is simply the average score, and we know that we add up all the scores, we divide by the number of scores, and then we generate the mean. That's probably our most basic measure of central tendency when you get, although notice that median is actually probably a little easier to calculate. The mean of our sample, and mode being the most easy to calculate, can be used to estimate the mean of the population on any given characteristic. So when we look at a sample, if the sample was randomly drawn from the population, then the mean of the sample should, if the sample is large enough, represent the mean of the population. That will rarely be the case in what we're doing in personnel selection. Right? We have a subsample. How did we come to that subsample of applicants? They self-select into applying for this position. How do they differ from the population? To the extent they differ from the population, we can expect to see a difference in their mean score from the population mean score, which is not really an issue for us in this context. The extent to which the sample mean deviates from population represents sampling error. So we can see, or it will show self-selection biases, what have you. Smaller samples can increase the size of this error, and this is why often we look at studies and we kind of dismiss studies because of the small sample size. And sometimes it's legitimate to dismiss these studies because of some small sample size, but sometimes it's necessary to work with a small sample size because there just isn't a large sample size available. Understanding the N, then, the number of measures within the sample, is what becomes important. The means of multiple samples tend to converge towards the actual population mean. That is, if we draw randomly multiple samples, take a mean from each sample, and then determine the grand mean, the combined mean of all those samples, then we see we get closer and closer to the population mean. So the mean of the distribution, notice, the distribution is the distribution. That's how the scores are distributed. The mean and the distribution are two separate concepts. So here's real three curves, and we see that the mean differs in each, right? But notice that the sample itself looks surprisingly similar, the sample of scores, right? So the mean has just moved. And this will become an important point here in a couple minutes. Now, a couple of the measures that we need to get under our belt is the measure of dispersion. And the range is the lowest to the highest score possible. And so we were looking at scores that went from 3 to 18, I believe, in the self-monitoring measure. That would represent the range. High of 18, low of 3. The range then would be designated as subtracting the lowest score from the highest score, which would have given us a range of 15, right? So the variance and the standard deviation, let's get to those in a minute. But the mean then is separate from the dispersion. That is, so the variance is different. The spread, right, it equals the average. Spread is high here, and the spread is low here. Notice that all three distributions have the same mean at 10, but the distribution of scores varies significantly. Very narrow range of scores, very broad range of scores, and somewhere in between. One important consideration if we're in a personnel selection process is, do we have enough range to actually rank people? Notice that if we have 100 applicants and they all score between 8 and 13, our measure hasn't done a really great job of necessarily differentiating those candidates. This would be a far better differentiation of 100 candidates than this would, all else being equal. So that's something to consider, and this is why we look at frequency distributions on measures we're testing or measures we're thinking of using. We can look for empirical research that's previously used those measures and see if it differentiates the sample enough for our process, for our purpose. Because ultimately we're about differentiating and rank ordering candidates. That's our ultimate goal. So the variance then calculates the distance of each person's score from the mean. So the first thing we need to do to calculate the variance is find the mean of the sample. And then what we do, and I know it's a laborious technique, I don't know if any of you have ever done this by hand. In some of my first statistics classes, we did samples of this by hand. And that is, we took the mean, right, of the sample, and then what you do is you just go down the column. This is person A's score, and you subtract, right, the mean from their score. So, and you're looking for the difference, and that is you end up with a column for each item. That is, to what extent is this different from the mean? What is this score different from the mean? What is this score different from the mean? And then from that we can calculate the variance. Now, the variance is always a positive number. It can't be a negative number, because within the process of calculating the variance, we square it. So even if it's a negative number, but a negative number squared is going to become a positive number. It's not very useful for our purposes, but it allows us to calculate the standard deviation, and that's ultimately what we want, is two things. Really need to know the mean of the sample, and we need to know the standard of deviation. It tells us a lot about the measure. So the square root then of the variance is the standard deviation. The standard deviation therefore relates more closely to the actual scores of our measure and becomes a more useful number for us to contemplate. Most normal distribution curves are 5 standard deviations wide. What does this mean? that when we have a distribution, and we can go through various procedures to normalize it, that we look at this very classic bell-shaped curve, and notice not all frequency distributions are like this, but this is where we go first. And so what we have is mu, and mu is a fancy Greek letter, right, or not, for the representation of the mean. So this is the mean of this sample, be it 10, be it 20, whatever it calculated, we're just going to use the variable mu to represent it. Now, what we see then in a normal distribution of this sample, we see that as we move away from the mean, this is the mean plus 1 standard deviation, this is the mean plus 2 standard deviations, and this is the mean plus 3 standard deviations, and then we can go the other way. Why is this interesting or important? Because it makes it possible for us to convert to percentages. And one of the big questions is, in kind of planning to hire new people, let's say we're hiring new people into an existing position where we already have tests. The previous hiring session, let's say, generated a lot of statistics about our candidates. That is, we brought in 100 candidates and we found that in fact X percentage of candidates scored in a range where we would actually consider hiring them. Notice how this works backwards kind of for planning. That is, well, how many people do you need to hire? Well, we want to hire 15 people into this position. And then I look at my past data in hiring and I say, okay, to get 15 people who scored at this level, right, then I actually need most likely to find X number of candidates, because 15 represents a proportion, that is a percentage of the larger number, right? So it allows us to do our planning, right, as well as determine who we'll hire and who we won't. Well, I'll be darned. Hi, Ursula. Come here, Ursula. Ursula doesn't come and visit up here very often, so that's interesting. Hannah's over here watching. Electron, come here. Electron, come here, sweetie. Come on. You want to say hello to everybody? Come here, Electron. Come say hello. There's Electron. Do you want to say hello?